So welcome back. This is our third video about the Markov networks, and I'm going to talk about energy functions. So it's very common that we express the joint probability of a Markov network in terms of energy functions. The idea is the following. We're going to say that the joint probability of the x variables, so x is a set of variables that we have in the Markov network, it's going to be 1 over z, and z is the partition function, an exponential of minus and the energy function that is defined over the variables of x. And it's very common to decompose this energy function in terms of local functions that they call the potentials. So in this course, we use the term potential effectors as synonyms, but it's very common for historical reasons that we call the potentials are simply the factors expressed in terms of energy. So yeah, in this case, the energy function will be a sum over those factors, and those factors are also defined for cliques that we have in the graph. So in this case here, it's going to be this psi of c, I forgot to include here, and xc. So if we put these two things together, and we have this equation here. So the probability of x, so the joint probability over all variables that we have in the Markov network, is going to be this long expression here. That's very similar to what we have before, but now we have this exponentiation here. And actually, it's just another way to express the same idea, because we can convert this exponential of sums into a product of exponentials. So just to make it more clear, we can think about this is going to be the probability of x is going to be 1 over z, and now we're going to move this exponential inside here, and we have to change the sum to be a product over all the cliques c of the exponential of minus, and we have this psi c xc. So now it should be very clear that if we call this psi c, I forgot to see here, xc to be minus log of phi c, again another c here, xc. So in the case that we change this guy here and we put this minus log here, the negatives will cancel each other. We will have the exponential of log that is going to be simply the this term here, the phi c xc, and in this case everything here just changed to phi c xc, and we have the Gibbs distribution exactly how we defined it before. So talking about these energy functions and talking about the Gibbs distribution that we had before is exactly the same thing. It's just another way to write the same idea, but now we're going to expressing with these exponential functions. And these functions are interesting because let me just erase here just to have a little bit of space. And if you think about those exponential functions, so we have the y here, and the x is going to be here, and it has this kind of shape here. So you go down and never touch the 0. So this is the exponential of minus x. So what is going on here? The first observation that we have is that in order to increase x, in order to have higher probabilities, we need to decrease the energy. So high probability is going to be equal to small energy. And another observation that is this function is interesting because we can put whatever we want inside these phi c xc potentials, and it can be positive or negative numbers. It doesn't matter what we put here in the x-axis, because we are computing this exponential function. It will never be 0, because as we increase x, this exponential of minus x is going to approach 0, but it will never touch the x-axis. So just to make it a little bit more concrete, we can look at the voltage example again, and this is how we defined the voltage example with those factors with numbers that are between 1 and 100. And if you want to compute that in terms of energy functions, what we can do is simply to compute the minus log of those numbers. So we saw in the previous slide that the psi c xc is going to be equal to minus log of phi c xc. So we can just compute the minus log of those numbers here. And we did that in the next slide. So here we are, and these are the new numbers. So it doesn't matter that we have a few zeros here, because when we compute the exponentiation, we will turn those numbers zeros into 1. So yeah, remember that it doesn't mean that we can have 0 probabilities, because we're going to compute the exponential first. So in order to compute the joint probability distribution, what we're going to do is to multiply actually sum those numbers together and exponentiate that later. So it's going to be something like this. We're going to take this minus. So in order to compute this assignment here, just to make it clear, you're going to take those assignments that are marked here. They're all compatible with this full assignment here. So it's going to be 4.61 minus, I'm summing, but summing negative numbers, 1.61 minus 4.61 minus 4.61, and that is minus 15.44. So we take this number and we need to calculate the probability, and we first calculated the unnormalized probability. That's going to be P2 is going to be of A not B, is going to be that assignment not C, D, and going to be equal to the exponentiation of minus, so I'm going to take minus and this number minus 15.44. And we're going to compute this, and going to be approximately this 5 million here that we have. All right, so we put this, and afterwards we sum all these unnormalized values and divide it. That's going to be the partition function, and we get the probabilities. Exactly like we did before. So let's take this idea of energy functions and see how it works in a small application. And I'm going to use the idea of pairwise Markov networks for this application. And the pairwise Markov networks is probably the most common type of Markov networks that we see in practice. It's basically a network that is defined over just two types of potentials, two types of factors, the node potentials and the edge potentials. So the node potential is going to be the factors that are defined over one single variable, and the edge potentials will be defined over a pair of variables. So as we're going to have this example working with images, we can expect that we have a grid, and each node will be associated with 1 pixel. And the fact that we have those potentials here connecting neighboring pixels, it means that we expect that there will be some correlation between those pixels. So if this pixel here has a certain color, I expect that this pixel here and this pixel here will have a similar color. And in this application, we can think that we have two images. One is a noise image, and the other one is a noise-free image that we will expect to get with our inference. So the noise image, we're going to represent that by nodes with Y, and the noise-free image with nodes with X. So in this 3D representation here, we have these two images. So we have on the back here the noise-free image with the X nodes, and they are connected together with these pairwise potentials. It means that we expect that neighboring pixels have more or less similar colors. But we also need to connect those nodes with the same pixel in the noise image, and we have another pairwise potential that we're going to connect this, right? So these are pixels in exactly the same position. So we have this X, Y xij and yij. So basically there are pixels in the same position for the noise free and the noise image. And we're going to observe those nodes here of the noise image. That's going to be our input. And we're going to make the inference. We expected that these nodes in the y here are going to influence our x nodes at the same time that the neighboring nodes should influence each other. And we expect to find the assignment that has the smallest energy, or in other words, that has the highest probability. So for many applications in image processing, we want to process the Markov network and find the map or the MPE assignment. So these are the assignments with the highest probability. This is so common that we call this the map MRF approach. So remember that MRF is Markov random fields. And basically it is the same as taking the Gibbs distribution and find the energy assignment that has the minimal value. So we assign the minimal energy with the assignment with the highest probability. The problem with this task is that there are too many assignments, so we cannot compute all of them. We cannot think about computing the joint probability over all the pixels, because if we think about the one small image that has just 100 by 100 pixels, so we have in total 10,000 pixels, and the number of combinations that we have, the total number of assignments for a binary image, just a black and white image, is going to be 2 elevated to 10,000 power. So the number of assignments is going to be huge. Okay, so instead of computing the joint distribution and finding the one that has the minimal energy or the maximum probability, what we're going to do is to use a stochastic search procedure. So these stochastic search are very simple search procedures that will start with a random assignment for all variables in the network. We improve the configuration using some local operations until we get into a position of minimal energy. Usually this position of minimal energy is local, so we are not able to find the global one, but sometimes this is a good enough approximation, and that is exactly what we got with this figure here, that we're going to use this figure and implement this code in the tutorials. So we started with this image that is corrupted with a noise, and we got this much smoother version of this image. So this is one algorithm for stochastic search, and we're going to check here the input is going to be a Markov network N with variables x, and we also need an energy function that we call E. And the output is going to be one assignment S for x that has the minimal local energy. So we expect it to have a position of a minimal energy, but we do not expect that to be global. It's possible, but it's very unlikely. So we need to start with one assignment, and this assignment must be complete. So we need to associate one value for all the variables that we have in the Markov network. In this case, we need to assign one value for each pixel. And we can do that at random if you want to, but that will take a huge amount of time to converge into something that is interesting, and it's more common that we assign to S the noise image. So I'm going to put a comment here that is common to use the noise image as a starting point for S. So we use an auxiliary variable here, xprev, to save the value for S. It's going to be useful later on that we're going to compute our convergence criterion and decide if we're going to stop or not. So let's save S for now, and we're going to iterate over a maximum number of iterations that we are calling I here. So when we reach this maximum number of iterations, we just stop the algorithm, but we can also stop using the convergence criteria. So what I'm going to do is use x prime to have a copy of the assignment S. You're going to iterate over all the variables that we have in the Markov network, or in this case, all the variables, all the pixels that we have in the image. And I'm gonna take one variable xi here and change its assignment. So I'm going to one pixel and change the value of this pixel. Once I have changed that, I will test to see if the energy of this new image that is very similar to what we had before with S, with just one variable that is xi changed, if the energy of this new assignment is smaller than what I had previously. If this is true, I'm going to take this new assignment and call it S. There is also another way of changing the assignments, and that's going to be a random decision. So usually this decision is based on the difference of the energy that we have between x prime and s, and if that is smaller than a threshold t, I will accept that. So this is frequently used so we can get away from local minima. So we usually go down in the energy landscape, but sometimes we accept to go up to see if we can get away from these local minimum points. There are many ways of implementing this, and we're going to discuss in the next slide 3 different ways that we can express this decision here. And remember that this for loop here is iterating over all variables that we have in the Markov networks. In other words, it's iterating over all pixels. So when we finish with that, we have finished with the image. And this is the point that we test this. This is a stop criteria for the algorithm. And we're going to see if what we had here before changing the image and compute the energy and check to see what is the difference to the new image. If this difference in absolute terms is less than the epsilon threshold, so we say that we have achieved the convergent criterion. So we're going to stop the search because we are changing the pixels, but the energy is not changing much. If it's not the case, we update the xpref to be x, and we're going to up and do another iteration of the loop until we get this maximum number of iterations or we achieve the convergence. So as I said, there are 3 main variations of the algorithm that we just discussed, the stochastic search. The first one is called iterative conditional modes, or ICM, and it selects the assignments with minimal energy. So it only accepts to go down in the energy landscape and never goes up. There is another variation that we call the metropolis, and we have a fixed probability that we call P, and we select one assignment with a higher energy according to this fixed probability. So we will go down, but we accept to go up in the energy landscape with a probability P. And there is another one that is extremely popular that's called simulated annealing, or SA. And the idea here is that in the beginning, I will be more prone to accept to go up in the energy landscape, but as we converge and the algorithm iterates, I will accept going to a higher energy point with a smaller and smaller probability. So usually we use this expression here, and T is a value that starts large and is reduced over time, and this delta E is the difference of energy between the 2 images, the one that I had previously and the one that I have just computed. So okay, so we saw in this application 2 ideas that are very common. One is the use of pairwise Markov networks, and the other one is the use of energy functions. So I guess it's good for now, and I'm going to have a small break, and we'll continue in the next video. So see you soon.